You are standing in a park. There is a sky above you, blue, convincing, lit from a reflective mirror system that tracks the sun. The grass is real. Children are playing somewhere down the curved path that bends upward at the horizon in a way that feels wrong until you stop noticing it. The air smells like soil and growing things. Somewhere in the outer hall, a micrometeorite the size of a grain of rice just punched a hole through 2 centimeters of aluminum. You have no idea where. Neither does anyone else. The air is already leaving. The Stanford Torus solves every human problem in space and creates an engineering problem no one on Earth knows how to fix. The design is not science fiction. It emerged from a serious NASA-funded study in 1975, developed by engineers and physicists who were not dreaming, they were calculating. A spinning ring 1.8 kilometers across, rotating once per minute, producing artificial gravity indistinguishable from Earth's at the inner surface. 10,000 people, parks, agriculture, manufacturing, a full closed ecosystem. Everything a permanent human presence in space would need. The numbers work. The physics is sound. The render looks like the future because, in the most technically honest sense, it is the correct picture of what a permanent space habitat would have to be. The gap between correct and buildable is where the problems live. Radiation is the first wall. Space beyond low Earth orbit exposes unshielded humans to a continuous flux of cosmic rays and solar particle events at doses that accumulate toward cancer risk over months, not years. The ISS sits inside Earth's magnetic field, which deflects most of that flux. The torus, in any useful orbit or at any Lagrange point, does not have that protection. Shielding requires mass, dense mass placed between the crew and the radiation source, thick enough to absorb the high-energy particles before they reach living tissue. The calculations for adequate cosmic ray shielding on the structure of the size of the torus produce a number measured in millions of tons. The entire International Space Station, assembled over 13 years by 16 nations at a cost of approximately $150 billion, has a total mass of around 420 tons. The shielding mass required for the torus exceeds that figure by a factor of several thousand. It cannot come from Earth. Launching millions of tons from Earth's surface is not an engineering challenge, it is a physical absurdity that no propulsion technology in development or projection resolves. It must come from somewhere else, an asteroid, the lunar surface, some in-space source of raw material that can be processed and positioned without a ground-based launch campaign. That supply chain does not exist. Asteroid mining has been studied, proposed, and partially funded, but no operational system has extracted and delivered raw material at industrial scale from any extraterrestrial body. Lunar surface extraction has been explored by robotic precursor missions, but the infrastructure required to process and transport millions of tons of regolith to a construction site in space has never been built. The torus cannot begin construction until that supply chain exists. The supply chain cannot justify its own construction cost without a customer large enough to use it. The torus is the customer. That circularity is not a temporary funding problem, it is the structure of the dependency. Assume the shielding problem is solved, assume future asteroid mining delivers the material, the construction begins and the ring reaches operational mass. The structure that results is a gyroscope. A 1.8 kilometer ring spinning at 1 rotation per minute has angular momentum that scales with its mass and its rotational speed. Angular momentum is conserved, which means any force that tries to change the direction of the spin axis is resisted by the structure itself. A gyroscope does not turn easily. The more massive and the faster it spins, the more force is required to redirect it. Every supply ship that docks with the torus delivers that force. Docking requires the ship to match the station's rotational velocity, make contact, and transfer its momentum into the structure. That transfer nudges the ring's spin axis. Active counter-rotation systems, secondary rings, or gyroscopic flywheels spinning in opposition can absorb some of that nudge, but they require power, they require maintenance, and they require that every docking event be carefully choreographed to minimize the angular deviation. Over thousands of docking events across a station lifetime measured in decades, the compounding cost of angular momentum management becomes a continuous engineering tax on every resupply run the station needs to survive. An orbital inclination change for the completed torus, the kind of maneuver that moves a station to a different orbital geometry, would cost more propellant than launching the entire ISS from scratch. The station's mass makes it almost immovable. Once the torus is in its operational orbit, it stays there. It cannot be repositioned in response to debris fields, changing mission requirements, or orbital decay from atmospheric drag. It commits to its orbit at construction and does not change it. For a structure intended to house 10,000 people across centuries, that rigidity is not a minor operational constraint. It is a permanent limitation on every decision the station's inhabitants will ever make about their relationship to the rest of the solar system. In 1991, 8 scientists sealed themselves inside Biosphere 2, a 1.27-hectare enclosed ecosystem in the Arizona desert designed to sustain them completely for 2 years without outside intervention. The designers had modeled the atmosphere, the soil chemistry, the water cycle, and the food production capacity. The structure was built with serious engineering resources and monitored continuously by a team outside the glass. Within months, oxygen levels dropped below safe limits. Carbon dioxide spiked unpredictably. Species that were supposed to stabilize the ecosystem died in patterns the models had not predicted. Insects critical to pollination collapsed. Crops failed. The crew lost significant body weight. The mission required outside atmospheric intervention twice before it ended. The closed biosphere degraded faster than every model predicted, under ideal Earth conditions, with a full support team watching from outside the glass. The torus proposes a closed ecosystem for 10,000 people in hard vacuum, rotating at 1 revolution per minute, with the nearest resupply months away, and no support team that can intervene in real time. Biosphere 2 had 8 people, a fixed orbit around the sun, breathable outside air available if the seals failed, and a parking lot full of engineers who could walk in with oxygen tanks. None of those conditions transfer to the torus. The ecosystem problem is not a scaling challenge that better models will eventually solve. It is a demonstration that biological systems in closed environments degrade in ways that modeling does not fully capture, even when the initial design is careful and the monitoring is continuous. Segmenting the atmosphere is the obvious proposed fix. Install internal pressure doors, divide the ring into isolated zones. If a breach occurs in one section, seal the doors and manage the loss in that zone while the rest of the population continues normally. The logic is structurally identical to the watertight compartments in a ship's hull, the same principle that kept the Titanic afloat long enough for lifeboats to be deployed. The atmospheric volume of the torus at operational scale is comparable to a small city. Subdividing that volume into meaningful pressure zones requires internal bulkheads massive enough to hold pressure differentials across a 1.8-kilometer ring while the structure is spinning. Each bulkhead penetrates the living space, interrupts the sight lines that make the habitat feel open, and disrupts the air circulation patterns that the agricultural ecosystem depends on for carbon dioxide distribution and oxygen cycling. The open sky, the defining feature that makes the torus feel like a place rather than a machine, is produced by the uninterrupted shared atmosphere. Segment that atmosphere and the sky becomes a series of enclosed rooms with no view of the ring's interior curvature. You have not fixed the breach problem. You have destroyed the habitat to fix the breach problem. This is the specific contradiction the design cannot escape. Every feature that makes the torus livable conflicts with a feature that makes it survivable. The shared atmosphere feels like real air and makes any breach a city-scale emergency. The spinning ring provides real gravity and turns the station into a gyroscope that resists every operational maneuver. The large interior volume supports a real ecosystem and creates a biological system too complex to stabilize from outside once it begins degrading. The design was optimized for human comfort with full engineering rigor. And that optimization produced a structure that is exquisitely difficult to maintain, nearly impossible to repair under failure conditions, and unable to be rescued if the failure progresses past a certain point. Maintenance is where the full weight of that contradiction lands. Every seal on the outer hull degrades in hard vacuum over time. Every structural joint accumulates fatigue from the continuous rotational stress. Every electronic system in the life support infrastructure requires inspection, testing, and eventual replacement. On Earth, this work happens with workers standing on scaffolding using tools from hardware stores, with replacement parts arriving by truck the same day they are ordered. On the ISS, it happens during carefully planned EVAs, with crews trained specifically for that hardware, supported by teams in Houston and Moscow who have the relevant schematics in front of them and can communicate in real time. On the Torus, it happens on the outer surface of a rotating structure 1.8 kilometers in diameter, in hard vacuum, with replacement parts that either came on the last resupply mission or will arrive on the next one, months away. A crew member who finds a structural anomaly on the outer hull during an EVA cannot call for a part to be delivered the next morning. The part either exists on the station or the repair waits. If the repair waits and the structure continues degrading, the anomaly becomes a failure. If it occurs in a shielding layer, the radiation dose to the section below begins increasing. If it occurs in a structural member, the rotational stress continues working on a weakened joint. If it occurs in the atmospheric boundary, the air pressure in the affected section begins dropping. The grain of rice micrometeorite that punched a hole in the outer hull on the first page of this script did not announce itself. It did not appear on any tracking system because objects below a certain size cannot be tracked from Earth or from the station. It hit at hypersonic velocity and created a breach that is currently venting atmosphere at a rate that sensors somewhere in the ring are beginning to register as a pressure anomaly. The breach is somewhere in a hull that takes a full shift to inspect on foot. The crew has procedures for this. The procedures require knowing where the hole is. Finding it takes time. The air does not wait. Your room in the Torus is on the opposite side of the ring from the breach. The sky above you still looks blue. The grass outside is still green. The children have gone inside for dinner. You do not know yet that the pressure in sections 11 through 14 has dropped 2% in the last 40 minutes, that the patch team is cycling through the airlock on the outer surface, and that the nearest backup atmosphere supply is locked in a cargo hold that was not scheduled to be opened until next week. The Stanford Torus is the most honest picture ever drawn of what permanent human life in space would need to look like. Every design decision in it was made by people who understood the physics and took the requirements seriously. The artificial gravity is correct. The ecosystem logic is correct. The radiation shielding requirement is correct. The scale is correct. What the 1975 study could not resolve, and what no study since has resolved, is the question of how a structure with those requirements gets built, maintained, and kept alive across the centuries it would need to operate to justify the cost of putting it there. NASA's current Gateway program, which is developing a small crewed station in lunar orbit to support Artemis missions, has a planned initial mass of under 100 tons and a crew capacity of 4. It is not the Torus. It is not trying to be. The gap between Gateway and the Torus is not a gap in ambition. It is a gap in every supply chain, manufacturing capability, closed ecosystem technology, and orbital maintenance infrastructure that would need to exist before the first ring segment could be welded in place. The Torus will remain a design study until those gaps close. What it demonstrates in the meantime is not failure of imagination. It is the precise shape of the distance between a physically correct answer and an engineerable one, and how little those two things resemble each other when the physics is working at full scale.